now going to model these data that deviate randomly from the trend structure that we formulated ourselves. So we know that in the data, the base development year trend is minus 20%. Calendar year trend between 78 and 82 is 10%, 82 to 83, 30%, 15% thereafter. And around that trend structure, I've simulated random numbers from a normal distribution with mean 0, and I think the standard deviation is 0.1, as we'll find shortly. So to model these data, let's go into the system. You might want to open your workbook 104A database. And we'll go to a triangle group called M3IR5. So I'll just click on there, then M, there it is. To open it, you might remember there's a number of ways of opening it. Control right mouse button. The right mouse button brings up what's called a context sensitive shortcut menu. And if you look at this shortcut menu, one of the options is to open. So we open the triangle group. If you open the triangle itself, we know that from 1983 going down, there's a 15% trend on a logarithmic scale. Yet if you look at the number 1989, it's larger than the number in 1990, development year 1. And the reason for that is you've got randomness around that trend structure. So successive numbers don't have to be larger necessarily. So if you look at this from the point of view of sales figures, you can see that due to randomness, if you've got a 15% trend, that number's not necessarily large. That number, because around the trend structure, you do have normal distributions. Okay, so I'm going to go back to the database. You can close the triangle. You don't have to open the triangle, have it open to model the data. You highlight it. When you open your triangle group, the pellet losses is immediately highlighted. It's active. You go to PTF tab, this one here, Probabilistic Trend Family Modeling Framework. And by default, two displays will be open. The model display. The model display represents the picture or 4 pictures of the model just estimated to the data. Along the development years, we've only estimated one trend. So you click on the development year title just to see that graph, and it's minus 20%, plus minus. Along the accident years, we have calculated the average level, one parameter, and along the calendar years, one average trend. What you can also do now is you go to the tile vertical button with the downward arrow and minimize regression tables. So it'll tile any display, but anything above regression tables, triangles, triangle groups, and database view, it will minimize. So it'll be 2 displays, the residual graph on the right side, the model display here. And we've got an average calendar year trend of 15.63%. Well, that's the average trend. But we know that in the data, there are in fact 3 trends. So we've got, for the early years, we have a trend of 10%, 30%, and then 15% for 8 years. So we've calculated an average of just over 15%, which is actually close to the true average. The true average would be something like 5 by 0.1 plus 0.3 multiplied by 8. I think it's 4 by 0.1 plus 0.3, 8 by 0.15 divided by 13, which is just over 0.15. Now, what's a residual? The residual is trends in data minus the trends estimated by the method. So if you now look at the residual graphs, let's maximize them, and let's just look at the residuals versus calendar year. Now, you've got a right mouse context sensitive shortcut menu. If you do that, you can see you can leave out the contours. Another way of removing the contours or bringing them in again, the shadings, is you can click on the space bar. Anyway, we know that in the early years, 78 to 82, the actual trend in the data is 10%. So the residual is the 10% minus the 15.63% in the method. So that's a negative trend of around -5. 82 to 83, we know that the data has a trend of around 30%. We subtract 15% from that, or 15.63, we've got a trend remaining of about 14, 15. Thereafter, we're removing a 15.63% trend from the 15% trend, so the resultant trend, the difference between the two, is around 0. Always think of residuals trending data minus trend estimated by the method. If the residuals have a trend of 0, then the trend in the data must equal the trend estimated by the method. Now this suggests to you that there's a trend change between 82 and 83 calendar years. And to insert a trend parameter between 82 and 83 on the x-axis, on the horizontal axis, you click on this gray box between 82 and 83 to introduce the parameter. Remember, the starting model only had one parameter in each direction. If you look at all the residual graphs, you have one parameter, trend parameter, along all the development years. A trend parameter is a parameter between years. To estimate a trend between years, you've got to have at least 2 years of data. However, for extant years, we have level parameters, intercepts like heights that might be reflective of exposures. There's only one parameter. There are no gray bands. If I put a gray band between 78 and 79, it would actually introduce a new parameter. So we only have one level parameter along the extant years. If I click on the residual graph versus calendar years, I've now introduced another parameter between 82 and 83. If I want to remove it, I just click again. So a new parameter between 82 and 83, and a new one between 83 and 84 that continues all the way to 91. So now along the calendar years, we have one trend parameter from 78 to 82, 82 to 83 is another one, and then 83 to 84 is another, to 91 is another one, that's 3. If you click on E to estimate, if you now click on model display, this is the model display icon. I mean, all these icons here, with time you'll learn what they are, just like trying to learn what's on the dashboard of a new car, what are the different buttons. So you click on the model display, and you can see that along the calendar years, our estimate of the 10% is not 10%, it's 8.73 plus minus 2. There's a certain level of uncertainty. If you look at your estimate of the calendar year trend 82 to 83, we put into the data 30%, but the estimate is way off. Also a lot of uncertainty with it. It's 39.27 plus minus 4.42. And the reason for a lot of uncertainty, and it's wide off the mark, is if you look at the residuals, the residual button is here, weighted residual plots, the one with the green diamonds. You will see that also in the LRF modeling framework. There are very few data points between 82 and 83, so we also have a large uncertainty. If you click back on model display, which is this button here, the one with the blue curve in it, you'll see that the estimate of 15 is pretty close to 15. So let's look at the model display. Versus development years, we've got a trend of minus 20%. Along the extant years, we have a level parameter of 11.5321. If you point to it, you can see an actual caption. It's the same with as development years. If you point to the line, the trend line, you'll get a caption. And along the calendar years, we have 3 trends. And if you want to look at the trend structure in the 3 directions, there's a 3D model display, which is this kind of surface-looking thing here, orangey-looking thing. If you point to that, it's on the right of the model display icon. If you click on that, within it itself, there'll be icons for different options. Now my computer here is pretty slow. So you've got a 3D model display, but that's the surface. If you actually want to look at the ribbons, can you see this button here on the top right here? Within the 3D model display, I'll resize it. Let's look at the ribbons. And now let's scroll it to the right. So that's the actual trend structure. To find the trend structure, you'll have trend structure in each direction, and these are the resultant trends. And you can see the kick up of the 39% or whatever, always one accident year earlier, development year earlier, sorry. And that's the kind of thing we saw in our PowerPoint display. The 15% always kicks in. Sorry, the 30% always kicks in one development period earlier, and you can see it in the 3D model display. Okay, around that 3D trend structure, if you close it, another integral part of the model is the fourth graph at the bottom right. If you click with the right button to get a shortcut context-sensitive menu, why don't we look at the standard deviation? So we're assuming that the standard deviation of the normal distribution by development year is constant, and it's 0.09. In fact, we generated data with an estimate with a standard deviation of 0.1. So the model display, the model itself is described by 4 graphs. If you remove any one of those graphs, you don't know what's going on in the data. The standard deviation of the normal distribution is an integral component of the model. You might remember with the coin that we tossed 100 times, the mean was 50. The roulette wheel numbered 0 to 100, the mean was also 50. So just knowing what the mean is, or having a good estimate of the mean, is not sufficient information. So in order to, for instance, to assess what the risk margin should be or the risk capital should be. So this is an integral part of the model. Do we have normal distributions? There's a button here, an icon. It looks like a magnifying glass with 3 diamonds around it. It's called Diagnostic Tools. Click on that. And we have some tabs within there. We're looking at diagnostic plots, weighted residuals normality plot. And you can see there's no evidence that we don't have normality in the residuals. Well, that's kind of good because we did simulate from a normal distribution. But notice the p-value is not in excess of 50%. We've calculated the R-squared or the correlation squared between our ordered residuals versus what kind of numbers we'd get if we ordered them and we were sampling from a normal distribution. So these on the vertical axes. On the horizontal axis, we actually have our residuals. We graph one against the other, and the graph should be linear if we've got normality. In fact, the R-squared is 98%. How likely we'd get an R-squared less than 98% had we've been sampling from a normal distribution? Well, it's pretty likely. The probability is 38%. So there's no evidence. If the probability was about 0.05, 5%, you'd reject normality at 5%. If it was 0.1, you reject normality at the null hypothesis normality at 10%. But I doubt that many people actually reject normality if the p-value is greater than 10%. If you click on the title of the graph, a lot of this is described in the manual. If you look at context-sensitive help, bookmark there, well, it also explains normality plots. Okay, so you've got an explanation of normality plot, which actually comes out of the user's guide, but the manual itself also has some explanations. Let's go back. Okay, let's close the context-sensitive help, topic help. Okay, if you look at the box plot just gives you a quick idea if there are any unusual observations, which we might call outliers. Well, there's one small one, but that must have been sampled from a normal distribution. If you want to look at a list of outliers, to click on the Outliers tab here. and the outlier is actually 1979 development period or development year 12. Let's close the diagnostic plots. Okay, we also have a regression table. So if you look at E's for estimate, O is a regression table, which is typically minimized when you enter the probabilistic trans-family module. But let's open it. It just tells you that we're looking at the old tab, which is all the parameters, which you can store right down, 3 sets of parameters. You can see the gammas are, by this picture, it's parameters along the development year. The alphas are parameters along the accident year, and the iotas are parameters along the calendar years, and there are 3. Now, I guess the model display kind of becomes redundant. If you close the model display, the regression table, it's kind of redundant because we now have a model display. If you close the regression table, it actually takes you out of the PTF modeling framework. So let's just minimize it. The regression table has been overtaken or superseded by the model display, which represents the regression table but pictorially, and it's quite much easier to glean the informational model. If you go to logbook, you're only going to learn this, we're doing this for the first time after we model quite a few different data sets. With time, you'll become more proficient in finding where the various icons are. The logbook is just a kind of summary of what's in the regression table. For instance, it tells you gamma last GL is -20 plus 1. That's the trend along the development years between the last 2 development years. But if you look at your model display, if you can't find it, you can always click on the icon, model display. You can see that when you look versus development years, there's only one parameter. That's really the trend along all development years, but the logbook only summarizes the trend between 12 and 13. IOTA last is the trend between the last 2 calendar years in the model. Back to the model display, click on development year trends, now calendar year trends, so you're only honing in on that particular one. You can see the 14.46% plus minus 0.46% is since 1983. Now, we go to forecast dialog box that you've met before. Click on that. Comes up with all of options that we'll go through in more detail as we analyze more data sets. But let me go through some of them. This triangle goes from 0 to 13. If you want to forecast further out, well, that's one option, which development year. In London, Equitas assumes the risk of the 92 in prior years, but the syndicates have got the whole triangle. They might be only interested in the reserves for calendar years 93 plus. Sorry, accident years 93 plus. Future underwriting years, pricing, well, it's another option. And you might remember that the calendar year trend projects in the accident year direction. That's an action. Another option is, do you want to continue with a 14.46% trend? Because if at the end of the year 1983, remember, you might not want to continue with the estimate of the 30%. So you've got development periods. Incidentally, you don't have to forecast from the first development period. You might decide to start your forecast at development period 7. And there are some examples when you need to do. Which accident years you want to forecast for. Automatic units, so you can select thousands, millions, billions. Do you want to use decimal points in the table? Last future accident period, that's if you want to forecast future underwriting years. You can go to future parameters. You can use inflation and discount rates. You can change the future IOTA parameters. Gammas you can also change. That's the trends along the development years. If you forecast beyond the last development year, you can exclude parameter uncertainty. You can store future or pairwise covariance correlations. Estimate statistics conditional on the next calendar period. We'll discuss that in another study. If you just click on OK, you get a forecast table. Now, what assumptions did we make in getting the forecast table? Well, let's look at the model display. We assume that that's the development year trend, including the uncertainty, accident year level, future calendar year trend. is a random number from a normal distribution with mean 14.46, standard deviation 0.46. I'm hoping you're not just watching the video, that you are in fact clicking on the various displays so that you'll learn how to navigate very quickly. Once you've done the forecast, there's a new icon called F, Forecast Table. So click on that. So we're going back to the forecast table. In the forecast table, the blue values are the observeds. We'd also assume if you go back to the model display, so that's good practice, that's the model display icon. We're assuming a particular standard deviation for the normal distributions. Back to the forecast table, so you go to F, it's on the right of the forecast dialog box. The blue is an observed value. The black is the mean of a log normal. On the right side of the steps, the black is the mean of a log normal. The red is the standard deviation of that. So for every cell on a log scale, we predict normal distributions, means and variances. On a dollar scale, we predict the corresponding log normal distributions. So each one of these is log normal. How do we know it's log normal? Because when you look at the diagnostic tools, good revision, diagnostic tools, the magnifying glass with the 3 diamonds, we have normal distributions for the residuals. Back to the forecast table, F. So we predict log normals for every cell, making explicit assumptions. These are all conditional, those assumptions. Future calendar year trend is 14.46, plus minus something. These are means and standard deviations of calendar years, liability stream. These are very important in calculating the cost of capital. What are these blacks? The black is the fitted mean, the total fitted mean by calendar year. And that's the total observed by calendar year. Okay, on the right side of the table, if you scroll to the right, you've got outstanding, mean, standard deviation, and the ultimate. That's the reserves. These are the ultimates, and the burgundies are the standard deviation. That's the total reserve. If you go to forecast summary, which is now FS, forecast summaries, you've got a forecast summary by accident year, mean, outstanding, ultimate, standard deviation, as coefficient of variations. You've also got the correlations by accident years if you need those. You probably won't, because, if you really needed those, you'll probably use the COM capability to take the system, to take these numbers seamlessly out of the system into another combinable product. Calendar year summaries, liability stream by calendar year. You've got observed versus mean estimate. So this is the observed, total observed by accident year. That's the estimated by accident year. That's the calendar year observed versus estimated. We then have some comparisons. So this is the total you paid in the last calendar year, excluding development year 0. That's your forecast for the next calendar year with its standard deviation. So if you look at the forecast table F, scroll to the left, you paid in the last calendar year $3.197 million. In the next calendar year, which doesn't include development year 0, you're paying $3.217. Now, a comparison would be the 3.197 minus the 580 to compare it with what you're paying in the next calendar year. And that's the comparison in the forecast summary. So if you go back to FS, forecast summaries, button, icon, FS, click on that. You've got that. You have some summary graphs. You've got forecast settings. Inflation is going out with 0. The future IOTAs, 14.4 for all the years. Let's not worry about the future variances. Click now on logbook, LOG. In fact, before when I went to the logbook, I kind of made a mistake by not telling you, exactly which icon it is. LOG, logbook. Okay, if you click on the logbook now, you'll see that the mean reserve is 23.4 million. The standard deviation of the reserve distribution. This is a start. We are if you go back to F, forecast table, to the right, we are saying that the reserve distribution, which is the sum of all these log normal distributions, which doesn't have a closed analytical form. That's why later on we'll be simulating from these log normals to find the distribution of the aggregate. We only do that because there's no closed analytical form for sums of log normals, irrespective of whether they're correlated. Okay, so we're now saying if you go back to the logbook, LOG, that the mean of the reserve distribution using those assumptions is that, and that's the standard deviation of the reserve distribution. If we now go to the residual graph, the one with the green diamonds, you can put in back the contours. You can click on the space bar. Give 0 weight to the last calendar year. I mean, we're doing this manually. In the next study, we'll do it automatically. Assign 0 weight to that year. Okay, so you click on the gray little box above the year at the top here to make it black. You click on E to estimate. So now you're estimating the same model, not using that year. If you look at the model display, that's actually now the trend between 83 and 90, which we're assuming continues to 91. Incidentally, let's go back to the residual graph. Let's undo this, the black, and re-estimate on E. You can see that we've estimated a trend of 14.46 from 83 to 91. If we remove this calendar year, we're removing observations that are a little bit below the 0 line. Our estimate of trend should increase. So you click on E. You then go to Forecast dialog box, the one with the yellow arrow, click on OK. So if you look at the forecast table, we've given 0 weight to the blue numbers in the last calendar year. We're still projecting this region without those data points. But we're estimating the same model. If you look at the logbook, LOG, and you scroll to the right, you'll see that now the trend has moved from 14.46 to 15.07. Your mean reserve is a little bit higher. The standard deviation of the reserve distribution is higher for two reasons. One, there's more parameter uncertainty, and two, your forecasting horizon is further away because you've taken your car backwards 1 year. Go back to the residual graph, the one with the green diamonds, weighted residual plots. Click now on the last 4 years we're going to give 0 weight to. This one, 1990, 89, 88. Make them all black. Click on E to estimate. Forecast dialog box, one with the yellow arrow. Click on OK. Now we've given 0 weight to the last 4 blue numbers in every accident year. The last 4 observations. Logbook is LOG. Scroll to the right. And we've got a mean of 20. It's gone up a bit, but so is the trend estimate to 15.63. So 4 years ago, the trend estimate had been 15.63. Today, it's 14.46. You want to know how well you would have forecast the last 4 years ago. So, let's see. You've removed the last 4 years. So, you've got predictions for all these cells. In fact, you're predicting normal distributions. Let's look. This is called validation analysis. Removing of years is called validation analysis, and you're really testing for the stability of the trend, not in the model, in the data. The model is supposed to represent what's in the data. We've estimated the model to the data. Now we're testing whether, in fact, it is true that that trend of around 15% is stable. If it's not, it's a feature in the data. If it is, it's also a feature in the data. Okay, we use models to find out what's in the data. So now you go to the V button. It's called validation analysis. It's probably the last time you'll, well, probably like to the last time use that, because later on we'll show you in a different study how you do automatic validation very quickly. So click on V, and you've got a plot, a graph of the prediction errors. For every cell that you left out, you've got a prediction, you've got an observational log scale, you also have a prediction of the standard deviation of the variance for that cell, so you've got scaled prediction errors. And you can see versus calendar year, prediction errors versus calendar year, there's a bit of skewness. You're doing a bit of over-prediction. It goes from -3 to 1. Why? If you go back to the logbook, 4 years ago you would have used a trend of 15.63. Today, using all the data, your estimate of the 15% is 14.46. So that sort of gives you a feeling that the last 4 years are a bit lower. Well, I didn't make them lower because I did use a trend of 15% since 1983. But in you modeling the data, you don't know. So what you do is you're going to test, we are going to test whether the trends has actually changed. So we go back to the residual graph, the one with the green diamonds. We add another parameter from 87 to 88. Now we need to undo all this blackness here, the 4 black years that we've zeroed out. You can do it in one fell swoop by taking a mouse to the left side, top here, with the gray little box, top right, just above the number 2 on the vertical axis, okay, above the number 2. Click on that. That undoes all the black. Click on E to estimate, E with the lightning. It's very fast. Now, go to the model display. Good practice, the one with the blue curve. And if you look at calendar year trends, you can see that the trend from 87 to 91 is lower at 13.39 with this standard deviation, 0.85. In the earlier years, the estimate of 15 is 15.82, higher. But if you point, the pink actually tells you there's no statistical evidence of a trend change. If you point to the line here, there's a caption. If you look at the caption, the last line in the caption, it tells you the T-ratio differences of these two trends between trend 87 to 91 and then 83. Okay, I'll just pause there for a minute. Let me put the mouse there again. It's telling us that the trend from 87 to 98 is 13.39%. That's what the caption is. It's now looking at the difference between the trend 86 to 87, which is the same as the trend from 83 to 87. And it's telling us the difference between those two trends, the T-ratio, is 1.4783. In other words, the T-ratio is small enough, it's less than 2, it's less than 1.96, whatever, that the 5% level, even at the 10% level, you would reject the null hypothesis that the two trends are the same. Okay? You'll also find the same information in the regression table. If you click on R, ERM, R on the regression table, you'll see if you click on the iotas, the T-ratio is -0.5. It's also pink. Minimize the regression table. Go back to the model display. I'm going to make it a bit bigger. Now, if you click on O to optimize, it will actually get rid of that parameter that we don't need. And we'll discuss this optimization in the next study. Okay, thank you for that. And okay, the next study will be, I guess, more interesting, and we're going to start revising more of these buttons.